This is one of the simpler kinds of moments questions we can look at. We'll look at ones where we have inclined rods in a later example. Okay, so first things first, as with any mechanics question, as we read the question, we're going to add information to the sketch provided, or if they don't provide one, we would create this sketch and then add information to it. So a plane KP is modelled as a uniform rod. So uniform, straight away we know that the mass of this, the centre of mass of this, is in the middle of the rod. Of mass 10 kilograms and length 8 metres. Okay, so straight away we know that this distance is 8. And we also know that 4 metres along this, there is a mass of, we can model it as having a mass of 10 kilograms acting through the middle because it's uniform. Okay, so the weight 10g is acting at a distance 4 metres. Okay. It is held in equilibrium by 2 supports at C and D. Okay, so if it's held in equilibrium there, we're going to have 2 more forces acting at C and D. AC is 0.5 metres and CD is 5.5 metres. I would probably write in that full distance as 6 metres just because it makes life easier to work through. Okay, so we've got all of our distances measured from A, that's helpful. A child of mass 30 kilograms stands at the point X such that the reaction force at C is twice that at D. Okay, so we don't know where this child is standing. We can kind of infer from this question, as the centre of mass is closer to D than C, but now the reaction force at C needs to be more, the child is probably standing quite close to C. So I'm going to draw that on the diagram. It doesn't matter if I'm wrong or it turns out to be on the other side of C. The algebra will tell me all of that. Just something so that I've got a diagram to be working with. Okay, so we've got all of the information on our diagram. The reaction force at C is twice that at D. So because the reaction force here is twice the reaction force there, I'm just going to call that reaction force R, and then at C I must have a reaction force of 2R. Now all of my information is on the diagram. I'm going to rub off this information. It's all on the diagram. We need to find that distance X. Okay, we want to know that distance. Cool. So let's have a look at how we can do that. We've got 2 things that we can use here. Moments and the fact that it's in equilibrium not just in terms of moments, twisting forces, it's also in equilibrium vertically. It's not accelerating up or down. That would also be true horizontally. However, we don't have any horizontal forces. Okay, so let's consider the vertical aspect first. So we know that vertically we have 2R going up there. Maybe just put a little note, we're considering the vertical forces. So we have 2R going up, and then we also have R there. Similarly, downwards we have 30g plus 10g, so 3R is equal to 40g. Okay, we'll keep it in terms of g for now. It may cancel down later, it may not. We don't care, keep it in terms of g for now. Okay, so R is 40 over 3g. Perfect. Now we'll consider moments. Looking at this diagram, all of our distances are measured from A, so it's probably going to be sensible to take moments about A. We know what these forces both are. We can now relabel this as 40 over 3g, and that one there is 80 over 3g. Okay, we can take moments about A. When I take moments about something in equilibrium, and everything you do in A-level maths will be in equilibrium, I know that the moments trying to turn my rod clockwise will equal those forces trying to turn my rod anti-clockwise. So if you imagine that we put a pivot at A, a hinge at A, those two forces are trying to turn it clockwise. These two forces are trying to turn it anti-clockwise. They must be in equilibrium. So we can say that 30g, the force there multiplied by the distance, so moments are always force times distance, perpendicular distance. Okay, so you see we're travelling across and down, so we're doing force times the perpendicular distance, x. Okay, we've also got another anti-clockwise moment. That will be force times distance. And that must be balanced by these forces times distances. So we're going to have a half of 80g over 3 added to 6, the distance of that one, times 40g over 3. Okay, we've got lots of numbers here. As we see now, the g does indeed cancel out. So it was nice that we kept it in terms of g. 30x is equal to, that's going to give us 40 over 3 plus 80 minus 40. Again, we've cancelled all of our g's. That gives us 40. So that gives us 40, 120, 160 over 3 is equal to 30x. X is equal to 160 over 90, dividing by the x. So we know that distance A to x is 16 over 9 metres. We were correct, it was just that side of C. It doesn't matter if you turned out in your diagram you had the wrong side of C, the maths takes care of all of that. Okay, so key things on this kind of moments question. Translate all of the information given to you into your diagram. Reaction forces, weights, uniform rod, stuff like that. If it's uniform, it acts through the middle. If it's non-uniform, you don't know where that force is acting through unless they tell you in the question. Okay, we then resolved vertically. Because we knew that forces down must equal forces up, it's an equilibrium, that gave us the value of R. Then we took moments. We can take moments about any point. We may have chosen to take moments about C to eliminate that force, but then we'd have to recalculate all of our distances. In this case, there was no real advantage to eliminating one force. So we took moments about A, calculated the clockwise moments, must equal the anti-clockwise moments, because it's an equilibrium, made X a subject, and solved. Okay, we'll just have a look at a similar question to this. So we'll just do the diagram and explain what's happening in the question. Okay, so we will have a uniform rod again, supported at 2 points. So A, B, supported at C and D. Okay, and then we'll have the child standing at point B. Okay, so we'll choose, let's have a 30 kilogram child again. And in fact, this time we'll choose to have a non-uniform plank. Okay, so still of mass 10 kilograms, but this time we don't know that that force is acting through the middle. What we're now going to be told is that this is on the point of pivoting about D. So if I just add in some distances to these, let's use the same distances. Okay, but now we have a non-uniform plank. Distance K, non-uniform, so we don't know it's acting through the middle. Okay, so we've got all of our information here. Now what I'm going to say is that the plank is on the point of tipping about D. Okay, so we've got a new setup. The child has now moved to point B, still 8 metre long plank. So everything's the same except for where the child is standing. The child is now standing at B. And we're now modelling it as a non-uniform plank. So we've refined our model. Okay, we want to find the distance K. Okay, so how can we do this? Well, we'll still add our forces to our diagram. So we've got a reaction force at D, and we might think that we would add a different reaction force at C. But if we think very carefully for a moment, we can realise that we know the reaction force at C. How do we know that? Well, if we think this is on the point of tipping about point D, it's just about to tip. So if we think about how much force it must be pushing down at C with, so if I hold this pen, it's just about to tip around that thumb there. There can be no force acting at C. If any more force here would cause it to tip, it's just lightly resting at C. It's not actually pressing down on it, and C isn't having to push it back up at all. So in fact, that force there is 0. There is only a reaction force at the point it's about to tip around. Okay, so now let's think, where should we take moments about? I'm going to take moments around D this time. I could figure out what that reaction force is, but I don't actually care. If I take moments around D, I'm going to do 0 times the reaction force at D, therefore eliminating any moments there. Okay, so let's work this out. I know that my distance there is 2 meters. So my clockwise force, clockwise moment, trying to tip it around D is 30g times 2. And then I also have this force here. So 10g multiplied by, well, I'm actually measuring that distance now. So it's not K, that's going to be 6 minus K as that distance. Okay, looking at this, K is my only unknown. I can cancel the G's. I get 60 is equal to 60 minus 10K. That tells me that K is 0. The centre of mass of this plank would be acting at A. Probably not the most realistic question ever, but that's the answer we get. Okay, the main point in this question is, if it's on the point of tipping about a point, you know the reaction force at any other support will be 0. That's the key message.